Alright, y'all, today we are talking about writing exponential equations given a graph. I am just going to start out by listing out some steps that we can use to find an exponential equation given a graph. We're going to start with this sort of skeleton equation. You don't have to call it skeleton equation or anything. It's just kind of a formula. F of x equals a times b to the x plus c. So this is our general exponential form that has our normal operations, right? Just multiplication and addition can be written in this form if we switch it up a little bit algebraically. So this is our general form for exponential equations. And it's nice because it's in the order A, B, C. We have a little mnemonic device to help us remember the order, and it is take a cab to the answer. The department made it up, but I think it's funny. The reason why cab is significant is that's the order we're going to find the variables in. So we're going to start by finding C, then A, then B. Step 1, C. So how might we be able to find a constant that's added on the outside of an equation? Well, when we add something on the outside of a function, what kind of transformation is that? It's a vertical shift, right? And if we think back to when we introduced exponential form, we had graphs with this shape and this shape. Both of these guys had horizontal asymptotes at y equals 0, right? So if we shift this up and down, right, if we have a vertical shift, our horizontal asymptote is also going to shift. So C, so for instance, if I shift this graph up 1, then my horizontal asymptote is going to change from being y equals 0 to y equals 1. If I shift it down 27, right, if I have minus 27, my horizontal asymptote is going to be y equals negative 27. So we can use the horizontal asymptote to find C. C is the horizontal asymptote. Two, we're looking for A. How might we find A here? Well, we want to, first of all, make sure we plug in C. And then, I'm just going to tell this to y'all now, and then we'll see why it works later. We're going to plug in C and the y-intercept. To find A. And then, last but not least, we need to find B. For B, we can plug in all the things we've found already. C, A, and any other point on the graph. To find B. Okay, let's take a look at this in our lab manual. This is the Equations of Exponential Functions section in the lab manual. Let's start off by looking at number 2. So our skeleton equation here is f of x equals a times b to the x plus c. So again, we want to find a, b, and c. We're going to start by finding c. C comes directly from our horizontal asymptote, right? So from here, we can see that c is just 3. Simple as that. So we can go ahead and plug in c here. So we have a times b to the x plus 3. Next, we want to find a. Now, in order to find a, we said we were going to plug in the y-intercept. Let's talk about why that might be useful. We have 4 variables here, right? We have output variable, right, f of x, a, b, and x. So we need to get rid of b, x, and f of x. Definitely, in order to get rid of x and f of x, we can plug in a point. We've done that before. That's super easy. But how do we get rid of b? Well, we need to make sure that we find some x and y value that get rid of b without getting rid of a. So since they're multiplied together, we can do that by making b to the x equal to 1, right? If we make it equal to 0, then this entire term is going to disappear, right? Because anything times 0 is just 0. And then a is gone, and that doesn't help us. So let's make b to the x 1. How can I make an exponential equal to 1? Let's think back to our exponential rules. Some base raised to what gives us 1? 0. Right? When our exponent is 0, we get 1. So let's plug in 0 for x here. A times b to the 0 plus 3. B to the 0 is just 1. F of x is, f of 0 is, right, the value of our function at 0, which is 5. So we have 5 equals a times 1 plus 3. A times 1 is just 1. We subtract 3 from both sides. We end up with a equals 2. So we found c, we found a by plugging in c and the y-intercept specifically. Now we need to find b. Right, that's our last variable. We have 2 times b to the x plus 3. Now we just have 2 other variables to get rid of before b is the last one. So we can just plug in any point on the graph, right? Other than the one we just used. So let's use this guy. It's already given to us. So -1, 11. So f of -1 equals 2 times b to the -1 plus 3. F of -1 is 11. So we have 11 equals 2 times b to the -1. What do our exponent rules say about that? Well, remember, a negative tells us that we need to take the reciprocal. So the reciprocal would be 1 over b to the 1, but b to the 1 is just b, so we have 1 over b plus 3. Okay, now we need to solve for b. Just some algebra left. So let's subtract 3 from both sides. We end up with 8 equals 2 times 1 over b. Let's sort of move this over here because we're kind of running out of space. So how do we get b out of the denominator? We can multiply both sides by b, right? If I multiply on this side by b, then we'll get rid of that fraction. And if I multiply this side by b, we just have 8b. So 8b equals 2. Then we divide by 8 to get b on its own, and we end up with b equals 1/4. Right, 2 over 8 simplifies to 1/4. So our final equation is f of x equals 2 times 1/4 to the x plus 3. Okay, so quick rundown of what we did. Remember, we found c equals 3 by using the horizontal asymptote. And we figured that out by thinking about transformations. To find b, we plugged in c, and also we let x equals 0 to get rid of b. And then, last but not least, we used any other point on the graph. To find b. All right, let's try this first one. So, again, our skeleton formula, we've got f of x equals a times b to the x plus c. The first variable we want to find is c, which we find by, again, just looking directly at our horizontal asymptote. Looks like our horizontal asymptote is at -2, so we have c equals -2. We plug that in. We have a times b to the x minus 2 here. All right, so we found c, now we want to find a, right? Take a cab. We find a by getting rid of b, which we need to do by plugging in 0 for x, right? We're plugging in our y-intercept. Our y-intercept here is -3/2. b to the 0 is just 1, which is why we used 0. We have a times 1, which is just a, minus 2 equals -3/2. We should add 2 to both sides. We end up getting a equals -3/2 plus 2 is just 1/2. We can plug that in. We've got 1/2 times b to the x minus 2. We're solving for b. Last but not least, we can plug in any other point on the graph for x and f of x. Let's use the one it gives us. So f of 2 is 1/2 times b to the 2 minus 2. F of 2 is 5/2, so we have 5/2 equals 1/2 times b squared minus 2. And then we start solving for b. So we need to add 2 to both sides. 5/2 plus 2 is 9/2. I can sort of undo 1/2 times b squared by multiplying by 2, right? So if I multiply both sides by 2, I end up with 9 equals b squared. To solve for b, I need to take the square root. So b is plus or minus 3. But if you'll recall, when we are looking at exponentials, our base b needs to be positive. That was from our short introduction to exponential functions in the converting between exponential and logarithmic forms video. So if we need to be positive, then we need to pick +3. So b equals +3, and our final function is f of x equals 1/2 times 3 to the x minus 2. So this is the answer here. One thing I'd like for us to notice is that this first one, we have this J shape, right, that has end behavior where off the graph to the left, right, as x is going to -infinity, we are approaching our horizontal asymptote. And as x is going to positive infinity, the y values are going to positive infinity as well, right? That type of exponential function has a base of greater than 1, right? If you'll remember from our last lesson, right? Because as these x values are getting bigger, as the exponents are getting bigger, we're going to be getting bigger as well. For number 2, right, our base here is between 0 and 1. It's still positive, but it's less than 1. This one, it's getting smaller as the x values get larger. So we have these two different types of exponential functions. All right, let's look at 3. So again, our skeleton formula is a times b to the x plus c. What is c here? Well, it comes directly from our horizontal asymptote. I think the axes here are shifted a little bit off. So we are going to go ahead and just assume that this is 5, right? That this has a horizontal asymptote of 5. We plug that in. A times b to the x plus 5. All right, in order to solve for a, we need to plug in our y-intercept. So we have f of 0 equals a times b to the 0 plus 5. F of 0 is 2. B to the 0 is 1 plus 5. A times 1 is just a, so we have 2 equals a plus 5. Let's subtract 5 from both sides. So we end up with a equals negative 3. We can plug that in. So we have f of x equals negative 3 times b to the x plus 5. So we want to plug in something for x and f of x, right? So that b is the only variable left and we can solve for it. So we can plug in any other point on the graph. Let's go for negative 2, negative 7. If you're given a point on the graph, you should usually use the point that you're given. It's not a great idea to sort of estimate because sometimes it's really close but not exactly where you're estimating. So, sometimes you will have to pull something from the graph, right? Look at, maybe an x-intercept or whatever. But if you're given a point, you should go ahead and use that point. So here we are working with negative 2, negative 7. F of negative 2 is negative 7 equals negative 3 times b to the negative 2. B to the negative 2, remember, that means that we need to take the reciprocal. So we have 1 over b squared, right? That's one of our exponential rules, plus 5. Okay, now we need to solve for b. Let's subtract 5 from both sides. So we have negative 12 equals negative 3 times 1 over b squared. In order to get b out of the denominator, we can multiply both sides by b squared. So we end up with negative 12b squared equals negative 3. We divide both sides by negative 12 to get b squared on its own. So we have b squared equals negative 3 divided by negative 12 is just 1/4. We take the square root of 1/4. And that gives us plus or minus 1/2. Again, we need to choose the positive b because we know that our base is always going to be positive. So our final answer is negative 3 times 1/2 to the x plus 5. Awesome. Okay, that's all I have for y'all today. Thanks, y'all.